All right, so the question then is, how can we resolve this idea of having a particle be made as having a specific wavelength, be made out of waves? Well, if we take a look at a sound wave that is made out of two waves that have slightly different frequencies, what we learned in Physics 2AB is that we're going to get a beating that takes place as the waves go in and out of phase with each other. And so we could think of this as being our beat frequency pattern for two similar waves. Okay, and so this is your, basically your average wavelength we could think of here, but being modulated by the interference between the two waves. If you take 3 or 4 or 5 waves and add them together, and then go to 10 or 20 or 30, what you end up is with something that just beats once. And then there are little tiny beats out here. So the outside beats become much smaller as you add more and more waves together. So this is basically then the superposition of similar waves to produce a wave packet. So this is kind of like what we saw with the photon. Remember, we kind of drew the photon as being something that had a typical wavelength that was the value for the photon's wavelength, but kind of had a finite length. And so that's essentially what we're looking at here. We're looking at color wave packet. And then we can say that the particle is the beat. So what we observe to be the particle is like the high amplitude part of this wave packet. But it's just a single beat, not a bunch of them. And then if you add more and more waves to this, you can end up with something that not only just beats once, but has a huge amplitude in a certain region of space. And so this would be a much wider distribution, or larger distribution of waves. Of different wavelengths. So it's like a delta function. But different waves mean different momenta. Because p is h over lambda. So the waves that are associated with this are waves that have a different wavelength, and so therefore what you're doing to get a particle that's well confined to a certain region of space is we are saying that we have no idea what the momentum is, because we're adding a bunch of different waves to produce this delta function. If you only have one wave, then you know exactly what the momentum is. But there's no beat, which means you're uncertain completely as to the particle's position. So here, we are very certain, there's more peaks, so we're very certain of the particle's position. but very uncertain as to the momentum. And so all these things can be put together into a single equation called the Heisenberg uncertainty principle. So that's what I'm driving at here, is by looking at these wave-like properties, we're led to the Heisenberg uncertainty principle. Okay, now, a result from statistical mechanics is that if you take a bunch of waves and add them together and they have different wavelengths associated with them, this is your result. And so this is just, it doesn't matter whether these waves represent the momentum of the particle or whatever. This is just to make a wave packet out of a bunch of different waves. This is the result. And so we'll just take this as a starting point, because this isn't a class in statistical mechanics, but K, you may recall from your experiences in 208B, is 2 pi over the wavelength. Okay, and so if we want to know what delta K is then, well, we can write delta K as, we could say, well, is delta K equal to 2 pi over delta lambda? A lot of people might say that, but that would be completely wrong. Okay? So what we really need to do then is say, well, dk, if k is 2 pi over lambda, then dk is minus 2 pi over lambda squared d lambda. Okay, so we're just taking the derivative of k with respect to lambda. This is lambda to the minus 1. That's minus 1 times 2 pi over lambda squared times d lambda. Okay, and for small changes in k and delta lambda, we can say that delta k is equal to minus 2 pi over lambda naught squared. We could say times delta lambda, if delta k, delta lambda are small. In other words, we're close to the slope of the, if k is 1 over lambda, we plot it like this, k lambda, k looks like 1 over lambda, and then we go from this point to that point, and this is delta k, this is delta lambda. And so that's close to the slope of the tangent line, which is dk d lambda, for small values of k and lambda. Okay, so that's why we can say this is approximately true, because it's close to our limit as delta lambda goes to 0 of dk d lambda. Okay, so we can rewrite this expression then as delta k equals minus 2 pi over lambda squared times delta lambda naught. And that would be the way in which we could connect in the difference in the k value to the difference in the wavelength. But we wouldn't want to do it this way. We wouldn't want to say that delta k is 2 pi divided by delta lambda. Here delta lambda is a spread in the wavelengths in the superposition. So we have to be patient here, because this is not the Heisenberg uncertainty principle yet, but we're getting there. Because if we take and multiply both sides of this equation through by h bar, let's define h bar, because we use it so often, as Planck's constant divided by 2 pi. Then h bar k is equal to Planck's constant over 2 pi times 2 pi over lambda, which is just equal to h over lambda, well, we already saw in the de Broglie hypothesis that that's the momentum of the particle, p. So h bar k is another way of writing the momentum of the particle. Okay, and so we could write this then, taking differentials of both sides, we could say, well then h bar delta k is equal to delta p. All right, and so now I'm going to do that to both sides of this equation. Do h bar delta k delta x is approximately equal to h bar over 2. Or, rewriting this as the change in the momentum, this gives me delta p delta x approximately equal to h bar over 2. And that's our Heisenberg uncertainty principle. Basically, what this tells us is that the basic properties of the wave are such that if you want to make the particle better defined in position, this is associated with a wider spread in the wavelengths. So that's what this looks like here. This is going to be a very small delta x times a very large delta p. What's delta p again? Well, delta p is just going to be h bar times delta k. So this is going to look like 2 pi over lambda naught squared times h bar times delta lambda. So it's directly proportional to the uncertainty in the wavelength. So that's equal to h bar over 2. But in this situation here, we've got a very small uncertainty in delta p because we only have one wave. And so that one wave has a well-defined wavelength. There's no spread in the wavelength at all, so delta p is essentially 0. Which means that delta x, the position of the particle, is infinitely uncertain. It could be anywhere in the whole universe with just a single wave. And so this is like almost an infinite number of waves to produce a delta function. Okay? You can do this in math with a Fourier series and you add, but you need a whole bunch of terms. So like the highest order terms you need to make something that is just a 1 everywhere except one place, and then a 0 everywhere else. Okay, and so those are then the extremal values for the how you would apply this to the uncertainty principle, and it comes directly from this idea of the more waves that you add that have different values for the wavelength, the better defined the position of the particle will be. And so how do we measure this delta x? Well, over here, we can think of delta x as, say, being like a standard deviation bounds. This could be when the wave drops down to, say, 1 over the square root of 2 of its maximum value. Or it could be 1 over e of its maximum value. Or it could be some other statistical definition. That would affect this constant here, depending on what kind of statistics you're using. But we're saying basically that the width of the particle, or the position of the particle, the width of this curve, is basically our bounds on where we're most likely to find the particle if we make a measurement. Okay, but the particle could be other places too. But it's more likely to be in this range that's defined by delta x from the statistical mechanics result. And so that's what we mean when we say here delta x, and so this is a certain characteristic change in the wavelength of all of the different waves that added together to make this wave. Okay, so this is all wave mechanics that's being used to define the uncertainty principle. But the uncertainty principle in itself is a way of telling us that you cannot simultaneously know the position and the momentum of the particle. So this is different from classical mechanics. And it's very important. The meaning of the uncertainty principle is that you cannot know the position and momentum to arbitrary precision. The better you know one, the worse you know the other. So what would be an example of this? Well, let's say that I'm trying to catch a butterfly with a butterfly net. Okay, so the butterfly is flying around, and so what I find then is if I move the butterfly net fairly slowly, the butterfly escapes. Okay, because I wasn't moving the net fast enough to catch it, but I wasn't disturbing the butterfly very much. But I clearly wasn't able to pinpoint its location well enough to catch it. Okay. But if I move the butterfly net faster, then I catch the butterfly, but I give it a much higher velocity. So now I don't have very much information as to how fast the butterfly was moving. Okay, so by moving it faster, I've given the uncertainty in the momentum of the butterfly a booster shot, because now it's got not only what its own momentum was, but the momentum of the net that I used to catch it. Okay, and so I'm more certain as to where it is because it didn't have time to get away. I was able to catch it when it was in a certain location. But it's at the expense of knowing how fast the butterfly is moving. Okay. On the other hand, if I don't want to interact as much with the butterfly has its own motion, which that I miss it because I don't know where it is. And so I haven't changed the momentum, the typical speed of the butterfly that much. But I don't know where it is because it's not in the net anymore. Okay, so that's kind of a simple conceptual example. What if we wanted to put a little more math into this? Let's say that, first of all, let's see how the wavelength of a particle relates to its mass. Let's say we have a baseball that's 1 kilogram. It's moving at 10 meters per second. Okay, so then the wavelength is going to be mass times velocity equals h over lambda. So the wavelength then for the baseball is going to be h over mv. So that'll be 6.63 10 to the minus 34 joule seconds divided by 1 kilogram times 10 meters per second, or 6.63 times 10 to the minus 35 meters. Okay, so we see then that, well, maybe this explains why we don't see the wave-like properties of baseballs. A baseball doesn't look much like a wave. The reason for that is that the wavelength is too small to measure. This is as much smaller as a bacterium. is, as a bacterium, is smaller than the galaxy. Okay? And so this is so many orders of magnitude smaller than anything that we can see. Actually, in terms of powers of 10, we're closer to the biggest thing in the universe than we are to this length, in terms of powers of 10. It's less orders of magnitude to get to the largest thing in the universe than to get to this kind of a small scale. Okay, and so this is way far away, way too small to measure. So this is why the wave-like properties of regular objects that we see sitting around us is not noticeable to us. But let's try the same thing for an electron. The mass of the electron, 9.1 times 10 to the minus 31 kilograms. We'll let it move at the same speed, 10 meters per second. So the wavelength then for the electron, I think you can see here, if we're dividing by a smaller number, that's going to kick the wavelength up to perhaps a measurable value. We punch that number out. We get 7.28 times 10 to the minus 5 meters. Which is roughly the thickness of a human hair. Depending on what kind of hair you have. Some people have thicker hair. That a micrometer would be really thin hair. It could be 10 times thicker than that, 10 to the minus 5. But this is roughly thickness of a human hair. And so this means it's quite measurable. As a matter of fact, that's 10,000 times bigger than an atom. So this wavelength then can be used to image small objects. And so that is the whole idea behind an electron microscope. Using the particles like waves to probe distances that are on the order of, well, many orders of magnitude, in this case, larger than an atom. We've actually gotten to the point now where we can measure atoms too, in terms of being able to see them, take pictures of them. But the electron microscope is a good example of where this wave-like property of matter becomes manifest for smaller mass particles, and not so much for larger mass particles. Okay, so let's use the idea of the uncertainty principle then to measure, let's say that we have an uncertainty in the velocity in our measurements. It's on the order of 10 to the minus 3 times the velocity. So we can measure the velocity, but only accurate to 1 part in 1,000, which is, what's that, 1/10 of 1%. Okay, so let's say that's our uncertainty in the velocity. Let's find delta x for an electron and for a baseball traveling at 10 meters per second. Well, delta P is going to be mass times delta V. Okay? And so in this case, V naught is 10 meters per second, and so delta V is 10 to the minus 3 times V naught. Okay? And so we can rewrite then delta X is equal to H bar divided by 2 times delta P, using the uncertainty principle. All right, so this is going to, remember H bar is Planck's constant over 2 pi. This is going to be Planck's constant, H, 6.63 10 to the minus 34 joule seconds, divided by 2 times 2 is 4 pi times delta P, so that's going to be the mass. This is for the electron. 4 pi times delta P, and so that's going to be the mass, 9.1 times 10 to the minus 31 kilograms times delta V. Delta V is going to be 10 to the minus 3 times V naught, which is 10 meters per second. This is the electron at 10 meters per second. So that gives us 5 times 10 to the minus 3 millimeters, or 5 times 10 to the minus 3 meters, or 5 millimeters. So that's a pretty big uncertainty. What does that tell us? It tells us that we can't even, in principle, determine the location of the electron to any more accuracy than 5 millimeters. It means even with infinitely accurate measuring instruments, if this is an inherent uncertainty in the velocity, then the uncertainty in the position is going to be this regardless of how expensive our measuring device is or how perfect our measuring device is. Okay, now let's try this for the baseball. Okay, for the baseball, delta x equal to h bar over 2 times delta p again. Okay, this is the mass of the baseball, so that's 1 kilogram times the delta v, 10 to the minus 3, times 10 meters per second. Okay, so everything's the same, except for this factor here, which is different by about a factor of 10 to the 30th power. So it makes a big difference in our final result. So this is 6.63, so then minus 34 divided by all this stuff. And that gives us 5.27 times 10 to the minus 33. meters. Okay, so we couldn't even tell if we were off by this much because we don't have any measuring instruments that to even within a factor of 100 trillion of this could tell if we were off by that amount. And so there's no measurement error. Due to this uncertainty in the velocity for a baseball. And that's why we don't notice this normally. But we get significant quantum effects when we deal with smaller mass particles. And so the uncertainty principle then tends to work better for the smaller types of subatomic particles.